as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists, and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
Hello and good evening to everyone. Thank you for joining us today. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 43rd webinar from the IRIS webinar series. My name is Richu George Philip and I'm a part of the Office of Global Engagement. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the Select Institute of Eminence. As you may be aware, IIT Madras has been ranked as #1 institute in India in both overall and engineering categories in NIRF 2021 ranking. IIT Madras has bagged the top rank in overall category for the 3rd consecutive year and #1 in engineering category for the 6th consecutive year. And in the newly launched category of research institutions, IIT Madras has been ranked #2 in the country. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway at IIT Madras. And as a part of these initiatives, the IRIS webinar series aims to showcase the innovative research being generated to various stakeholders like the students, researchers, industrialists, and policymakers. From the Quantum Science and Technology cluster, the research initiative presenting today is Quantum Information Theory, led by Professor Arul Lakshminarayan. Quantum information theory has seen remarkable contemporary developments. Theoretical and mathematical aspects of QIT and how it illumines states of matter and of the nature of space-time and quantum gravity is the wide gamut of this center. Professor Arul is a professor and head of the department at the Department of Physics, IIT Madras. A theoretical physicist, his research interests are in dynamical systems, especially Hamiltonian and quantum chaotic systems, quantum information, especially entanglement, many-body physics and thermalization, random matrix theory and its applications. Professor Arul graduated as a mechanical engineer in 1988 from IIT Madras, following which he did his PhD in the State University of New York at Stony Brook in theoretical physics. He is a long-term visiting scientist of faculty on Washington State University at Pullman, IIT Kanpur, the Max Planck Institute for the Physics of Complex Systems, Dresden, Germany, and the Smoluchowski Institute of Physics, Jagiellonian University at Krakow, Poland. He specializes in theoretical aspects of quantum information and dynamics, random matrix theory, and quantum many-body physics. And as the moderator for the event, we have Professor Karol Szyszowski with us today. Professor Karol is a physicist, co-author of the Square Root Voting System for the Council of the European Union, a skiing guide to the Tatra Mountains, and a monograph on geometry of quantum states. He is a professor at the Institute of Theoretical Physics, Jagiellonian University, Krakow, Poland, and also at the Center for Theoretical Physics, Polish Academy of Sciences, Warsaw. Since 2019, he is the director of the Quantum Information Center in Gdańsk. He has co-authored with I. Bengtsson the book Geometry of Quantum States, An Introduction to Quantum Entanglement with Cambridge University Press. Thank you for being with us today, Professor Karol. We're very excited that you could be a part of this session. We also have distinguished panel members from various departments at IIT Madras. We have Professors Dr. Ayan Mukhopadhyay, Dr. Kunal Krishna Mukherjee, Dr. Lakshmi Bala, Dr. Prabha Mandayam, Dr. Pradeep Sarvepalli, Dr. Rajesh Narayan, Dr. Sunetra Ramanan, Dr. Suresh Govindarajan, and Dr. Vaibhav Madhak on the panel with us today. A warm welcome to all of you. So before we start, a note to the participants, please use the Q&A box to enter your questions and upload questions that interest you so that Professor Carol can prioritize them later. Over to you, Professor Carol.
Thank you very much, Rachel, for that lovely introduction. Let me say hello to all of you who are joined us this evening. What I'm going to do is share a presentation initially for about 15 to 20 minutes, in which I will highlight what we are planning to do in this center, what we have already initiated a little bit, and introduce my colleagues. And I should also say, of course, that I'm really excited and happy to have colleague, friend, and an expert in quantum information here as a moderator, Professor Carol Shishkowski. So those of you who have questions, I think there is no better authority on this subject than Carol. So please make use of this time, although it's very brief, I do agree. So let's start without further ado. Let me share my screen. Yes. So the center which I'm going to talk about is the Center for Quantum Information Theory of Matter and Space-Time. And as a presenter, I'm actually representing colleagues from the departments of physics, electrical engineering, and mathematics here at the IIT Madras. So these are the faculty cast. There are actually 10 of us. And Professor Lakshmi Bala, Suresh Govindarajan, Prabha Mandayam, Pradeep Sarvepalli, Vaibhav Madhok in the top row. Of these, Pradeep is in the Department of Electrical Engineering. Others are in physics. And those of you who were students here or are students here will, of course, recognize many of my colleagues who have been here for many years as well. And in the lower row, we have Ayan Mukhopadhyay, Rajesh Narayanan, Kunal, Sunetra, and myself. Kunal is from the Department of Mathematics. The others are my colleagues in Physics Department. And we come with very different backgrounds. So there are high energy physicists, string theorists, quantum information theorists per se, condensed matter physicists, condensed matter theorists, nuclear many-body physicists, algebraists, mathematicians, people who have specialized in quantum chaos, many-body systems, and so on. So it's a very interesting and a unique combination of people, I think, who have come together to understand to further study the implications of quantum information, which itself is a very broad area and a kind of an umbrella. And of course, all of this activity, there is a very large, committed, and excellent set of graduate students, PhD students, undergraduates as well. But what you're seeing here on the screen is a sample of PhD students mostly. Some of them are also postdocs. In fact, this is before the corona. That's why you're seeing this particular ensemble. It was just before the corona. You can see this lovely banyan tree. Those of you who know IIT Madras, this is in front of the CLT. And some of them have now gone on to become faculty members or postdocs elsewhere. And so that's the set of students and postdocs. So what exactly are we interested in doing? So what we are, our menu, so to speak, is that any significant open problem that's, of course, interesting to us and of fundamental interest in quantum information theory. And just not pure quantum information theory as such, but also in how it is informing about the states of matter, and actually the very nature of space-time itself. There are very, very exciting developments currently underway which link these things, and we hope to study this further. In fact, as I said, quantum information theory itself is a rather interconnected series of field, and its inputs are from quantum physics, of course, information theory, whose origins were in the 1950s due to Shannon, computer science, as well as mathematics. So we have roughly kind of divided ourselves, although this is only for some organizational purposes, into three different categories. So the first one is mathematical aspects of quantum information. So we kind of propose to study in interesting states called absolutely maximally entangled states in that, quantum codes, mutually unbiased basis, tensor networks, entanglement, holography. So all of these things are just a few bullet points, so to speak, of what we intend to study under these mathematical aspects of quantum information. Quantum dynamics, matter and information, is the second part. Quantum chaos, many-body physics, tomography, which is understanding the states of quantum systems and measuring them. So that's the second part. The third part, fields, space-time, and information, is about quantum fields and the study of quantum gravity. Black holes play an important role in this, information locking, phenomenon algebras. So this is another aspect of this. So all of them really come together in some sense, as I said. And also, I must say something, because when, as you know, theorists, our problems and what we look at in calculations evolve with time. So whenever we are asked for what you're going to do over 5 years, it's a very difficult question, because we'll be happy to know what we're going to do in the next 6 months. Because if we know the calculations which we're going to do in the next 6 months, we're probably not doing our job too well. So a theorist thing changes with time quite rapidly. So our interests and our calculations and the way in which we are doing things will also change. But what we have put down here in this T1, T2, T3 are guidelines for what's going to come. So I understand that it's a mixed audience. So I'm going to give a bit of an introduction first before I talk more jargon, so to speak. Okay, so really, as you know, the foundation, the foundations of quantum mechanics was laid by Schrödinger very early on in the 1920s, along with Heisenberg and others. And Schrödinger was one of the few people who realized very early on the very different nature of quantum mechanics. And he understood very well the crucial property of entanglement. And he says in this first paragraph, and I will just read it out to you, when two systems enter into temporary physical interaction, and when after a time of mutual influence, the systems separate again, then they can no longer be described in the same way as before. I would not call that one, but rather the characteristic trait of quantum mechanics. So, and this is the one that enforces its entire departure from classical lines of thought. By the interaction, the two representatives have become entangled. So what it's saying is that if two systems interact once, that's about it. They are together forming one holistic entity, which is entangled. And it may be difficult to talk about the individual states. So that's in the next paragraph, which says that the best possible knowledge of a whole does not necessarily include the best possible knowledge of all its parts. So this sounds a little bit philosophical, but just think about it. It's a little bit mind-blowing, because it says that you can have a knowledge of the entire system, but it does not necessarily include the parts. We assume that if you know the whole, you know the parts. That's not really the case in a quantum system, even though they may be entirely separate. It is rather discomforting that the theory should allow a system to be steered or piloted into one of the other types of the state at the experimenter's mercy, in spite of his having no access to it. So this was as early as 1935, and this was in response also to the writings of Einstein, Podolsky, and Rosen in what is today called the EPR paradox, so to speak. So let me just give you an idea of what is involved here. Let's take two coins. Just think about two coins, head and tail. Okay, so each of them can be in one of these states, and there are four possible classical states. Both of them can be head, head, tail, tail, head, and tail, tail. That's it. We are done. What quantum mechanics says, however, is that you can have states such as what I've written below, namely head, head, plus tail, tail. So if you look at this plus, that's coming because of superposition of quantum states. And if somebody asks you, what is the state of a single coin, let's say the first one in the state, it's actually hard for you to say whether it's head or tail. In fact, it is neither. Only measurement will reveal for you whether it is head or tail. So this kind of a state is an example of what Schrödinger was grappling with in 1935, and already recognized that this was a very different kind of state from what we are used to in classical mechanics or classical states. So these have, in fact, that was 1935. We are nearly 100 years later. Why is this at this point of time so crucial? Is that a lot has changed by way of our understanding of entanglement, both in terms of theory and in terms of experiments. So now we can actually control many of these things which were at that point of time basically only a matter of thought, let's say. So here I've illustrated what is a qubit, which is a central actor in this play. And a qubit is basically a quantum two-level system. There are two accessible levels to a quantum system. So in this picture, I've shown there is a ground state, S half, and there is a D excited state. And these two states would be the states of the qubit. So the particle, let's say an electron, can be either in this S state or in the D state. So if it's in the S state, we'll call it the zero, that's like the head. And the D state, we call it tail, that's the down state. Okay, so there are only two possible states as far as this quantum system is concerned, but actually all superpositions of it, alpha 0 plus beta 1, are also physical states, although there are only these two states as far as energy levels are concerned. So this superposition, what I've called 1, is at the center of quantum mechanics in terms of superpositions. If you have more than one such atom, let's say you have two of them, then they can be in this state in which both the atoms are in the ground state, 0, 0, plus both of them are in the excited state. So you see that it's like the head, head plus tail, tail state. And you can add more atoms. If you have 3 atoms, they can get entangled in a very strange way. And this is, so by the way, the earlier state is called a Bell state, and the one below is called a G and Z state, in which all atoms are in the ground state, 3 atoms on the ground state, and that's superposed with a state in which all 3 are in the state above. So these states are all extremely non-classical states, and they lead to very interesting consequences. What are these consequences? So there's been many milestones I'm just very briefly pointing out a few of them. Surely there are many more. So Bell inequalities was actually what was sort of in the realm of speculation or philosophy was taken into the realm of experiment in science when John Bell pointed out how one can test the assumptions of what is called locality and realism, which is underlying Einstein's view of what quantum mechanics should be into the laboratory. And entangled states violate these assumptions. And in fact, today it is acknowledged that from various experiments that it is violated. And indeed, quantum mechanics violates these assumptions of locality and realism. And that is, Bell's inequality is violated by such entangled states such as the Bell states and the G and Z. There's a no cloning theorem along the way in the 1980s. There was a no cloning theorem which says that you cannot copy an arbitrary quantum state. unknown quantum state. So there's no quantum Xerox machine, so to speak. You can't put any, so these have very important consequences and limitations. Quantum teleportation, which sounds a bit like science fiction, but it actually uses this entanglement to teleport the state of a quantum state, of a particle in a semi, in a very interesting way, where one only transports two classical bits of information, and along with entanglement, actually, in effect, transfers an infinite amount of classical information. So this is a very interesting, but a very central protocol of quantum information. Quantum cryptography, how to protect information. So this is, again, entanglement plays a very important role. Quantum computation, quantum computers are in the air. So this is, in fact, what led to a lot of fillip for the study of the subject. There were especially two major algorithms in the 1990s, which were developed using quantum mechanics, showed factorization of large numbers and Grover search algorithm. Both showed the power of quantum computing over the classical. And in fact, so much so that now we talk about qubits on the cloud. So you have a Google Cloud, and you can access for free 5-qubit quantum computers and do these kind of computations today. And there are at least up to 53 qubits that are accessible if one wants. So I should say that for each of the qubit that's accessed, there are two states. So something like 53 qubits has 2 to the power of 53 states. It's a very large number. Okay, so what is interesting about this? As I said, entanglement is an interesting quantum property, and entanglement is also a resource, is what the party line is, and it's a resource for doing many things like teleportation and so on. But I should also say at the outset that states which I have written, like the Bell state and the GHZ state, are in fact examples of what is called maximally entangled states. So you can have not only that the states are entangled, you can have also a measure of entanglement put to that. And you can find out how entangled states are. And these are examples of maximally entangled. You cannot go beyond that. And here is a book by our moderator, Karol Szyszkowski and Ingemar Bengtsson, Geometry of Quantum States, now into the 2nd edition. So I'm especially pleased that the picture on the 2nd edition has changed from the first. And well, not that the first was an uninteresting picture, but it's changed. And now it is a what's called a Borromean ring configuration. So there are 3 rings such that if you look closely, no 2 of them are actually linked. If you just ignore any one of the rings and you look at the other 2, you will see that they are just lying one on top. One is lying on top of the other or on the bottom of the other. They're not linked, but actually all 3 of them are linked together. So this is a classical illustration of what is the entanglement properties in a state like the GHZ, where there are 3 particles in the ground state and 3 particles in the excited state, and they are superposed like this. So no 2 of them are entangled, but they all have maximal entanglement. They are multipartite entanglement. So the understanding of such entanglement is a very important part of quantum information science. They are used for teleportation, as I mentioned. They are used for constructing error-correcting codes, secret sharing, dense coding, various protocols which use such unique quantum states. By the way, there is a picture below the covers, a picture which is in a temple quite near me here. And you will find in a pillar the Borromean triangles from this somewhat ancient temple. So it's actually these Borromean rings go back in a cultural sense to many cultures and across time. So it's very interesting that they also, it's not as if the GHZ rings are in this configuration. I mean, the GHZ state is in this configuration. It's a way of thinking about these states. But what is interesting, if you take 4 of these qubits, can one find maximally entangled states in a particular sense? And it turns out that actually they do not exist. You may think of whether all 4 particles are in the ground state and then 4 in the excited state. It turns out that this is not a maximally entangled state in that sense. So when you add more particles, the nature of entanglement gets very interesting, and that's part of the contemporary study of this. Okay, so we are interested in quantum information theory not just for itself, but also in how it is describing matter in space-time, as I said. Qubits, which are just 2-level systems, are very nicely described by the spin systems, or spin half in particular. You might have seen these as underlying magnetic structures. So spin chains as quantum devices. So in fact, collection of spin chains as quantum devices is one of the models of quantum computer. And these spin chains can have, as I've tried to indicate here with these circles, different kinds of entanglement among these. So now it's not just 2 or 3, but actually many. And we are asking about their entanglement in very fine questions about their entanglement. It turns out that this is very important in condensed matter systems or many-body physics. So in particular, the description of quantum phase transitions, where by changing a parameter like pressure, you would end up with very different kinds of matter, or you could change a magnetic field. So instead of changing a temperature, which is a usual phase transition when you have, let's say, water to ice kind of transition, here it's a parameter, and these fluctuations are quantum-driven fluctuations. So quantum phase transitions are witnessed by entanglement changes. One of the new ways of looking at these things is what's called many-body localization, and entanglement plays a key role in this. In fact, many-body localization may be a necessary condition for a good operating quantum computer. Quantum chaos and thermalization, you want to avoid maybe quantum chaos in a computer, but nevertheless, it plays a very important role in thermalization. And also entanglement plays a crucial role in our understanding of these. In atomic and nuclear systems, in which all of these, you have many-body systems, they are natural many-body systems. And space-time is a little bit speculative at this point, but actually there's been very remarkable developments which are linking string theory entanglement and quantum gravity, which is, in fact, string theory is a theory of. So I just want to mention some words here. There are these very pretty pictures which I've put on top. The one with the fishes here is a picture from Escher, and it's a description of what's called a hyperbolic space. And actually, all the fishes here are of the same size. What you're seeing here is an effect due to the curvature of the space. And this is a model of a space, and which is called the ADS. And a holography is a description of a connection which one of the connections is what is called now ADS CFT. So ADS is a quantum gravity theory. A CFT is an ordinary quantum theory in which we can describe entanglement and so on. But this is at a boundary, and this is in the bulk. So this holography is telling you that you can say something about the bulk by looking at what's happening in the boundary. And entanglement plays a crucial role in this, in the entanglement of these quantum theories on the boundary say important things about gravity itself. And there are many body models which are called tensor networks, which are models of quantum gravity. Black holes, a central kind of character in quantum gravity, is a very interesting object, which is also we are studying. Space-time itself as a quantum many-body phase. Okay, I think I am now nearly at 5:30. So what I have introduced here is a background, and what we intend to do is study these absolutely maximally entangled states, which then lead to perfect tensors in these which can be used in these tensor networks. establishing the very existence of absolutely maximally entangled states, their analytical construction. And we will also be looking at new quantum error correcting codes from tensor networks and some of the open problems about the existence of mutually unbiased basis, which impacts into the study of complementarity and incompatibility in quantum mechanics. And in terms of the second section, we'll be studying things like scrambling of quantum information, which is how, if you put information into a local system, how it spreads into the many-body system. And quantum chaos, out-of-time order correlators, entanglement indicators in nuclear many-body systems, which is actually very less investigated, more toward quantum simulations as such with the existing quantum computers. In the third part, holographic approaches to disordered systems, holography, tensor networks, as I mentioned, entanglement in quantum field theories, and quantum commutation relations and the von Neumann algebras. So I think I should stop here and ask for questions because I've run out of time. But I just want to say that we have made already, along with the group of Professor Karol Szyszkowski, some inroads into the existence of, for example, absolutely maximally entangled states in cases where it was not known before. And this actually is in a paper which is called 36 Entangled Officers of Euler. Those of you who are curious can take a look at it in the archive. It's something like a Sudoku kind of a puzzle, but now entanglement plays a crucial role. So there is quantum error correction. I'm just going to run through these slides of my colleagues who are like here, my colleague Prabha Mandayam and her students, as well as Pradeep Sarvepalli, work on quantum error correction, which is very important for, of course, the working of a quantum computer, and quantifying incompatibility, as I mentioned before, uncertainty relations, and so on. Pradeep, who is working from the electrical engineering, is involved in quantum coding theory, fault-tolerant quantum computing, quantum algorithms, secret sharing, and so on, topological codes. Professor Lakshmi Bala and her students and co-workers look at what are called continuous variable systems. I've talked about qubits, which have only 2 levels, but if you have studied quantum mechanics, you would know from a harmonic oscillator, it contains infinite number of levels. So these are, they are studying what's called tomograms to determine the state of such, how to optimally determine the state and how to infer properties about entanglement and other interesting properties from this. As I said, entanglement many body systems. This is Professor Ayan Mukhopadhyay. We're talking about string theory and quantum information theory in fields. So there are many, many publications. I just note here a series of them. You will find them. We have a preliminary website on, but you're welcome to see our papers. Most of them are available in the Quantum Physics Archive on a variety of different topics. So I thank you for your attention.
So good evening in India, good afternoon in Poland. It's my great pleasure to be here virtually with you. And I enjoy very much this event. To be honest, I'm a bit intimidated. I was never talking about quantum mechanics to the audience of more than 600 participants. It's unusual in Poland, but in India, as I see, it's great. I was enjoying reading all the questions. There are many questions already written. I just start to answer some of them, but let me now go to the most important and basic questions. I think it is formulated at the very beginning. What exactly is quantum theory? Why it is so complicated? So Arul, would you like to share your opinion about it?
Karol, I have spoken for, I think you should please take this.
Okay, so let me make a short attempt. Even though the second question is, could you please give a short answer, what is quantum information? This is not simple. Really in 2 sentences, this is the theory which concerns micro world. If you have macro world, you see my pen, I know exactly where it is, I can measure it position, and its velocity if it goes down. With small particles, it is not possible. Therefore, quantum theory is a probabilistic theory. The question where a particle is located is not suitable. We ask question, what is the likelihood it can be measured in this or other place? And therefore, it is a probabilistic theory which allows us to answer a basic question, what is a probability of certain outcomes of measurements? And it is complicated because it uses relatively advanced mathematical tools like complex numbers, complex vectors, and matrices. So this was first question. Second, I think very much related. Somebody wrote, is quantum theory used in physics different or the same as in quantum chemistry? Of course, the basic assumptions are the same. The quantum physics is the same, but the questions posed are different. In physics, we discuss really the basic ingredients of the nature of materia. In chemistry, they use quantum tools. In quantum, the same Schrödinger equation, which tells us how the probabilities evolve in time to understand structure of chemical compounds. Okay, let me continue browsing another interesting questions. So there was another question, what exactly is quantum entanglement? Of course, it was already answered, presented in the presentation by Arul, but let me only remind you. If you have two subsystems, like two pens, in probability theory, we can say some variables are not correlated. If you have two coins and we toss them simultaneously, standard classical coins are not correlated. The probability that you will get, let's say, heads on the left coin is not correlated with results on the right coin. So quantum entanglement is exactly, there are strong correlations between both quantum subsystems, as simple as that. So highly entangled Bell states, it means that they are very strongly correlated. Exactly, most correlated means that if you observe, for instance, let's say heads in one coin, you will also observe heads, or maybe if the state is like this, the Bell state, there is a perfect correlation between outcome of two independent results. Now, the question is why entanglement is important in quantum computing, and what is the relation between quantum information, between information theory and quantum. So in standard information theory, we work only with zeros and ones. So we have a sequence of zeros and ones. So all our information can be stored as a sequence of zeros and ones. However, in quantum theory, there are states like 0 and 1, but there are also all superpositions, like a little bit of up, a little bit of down. So the spin or the qubit is any physical system which lives in two-dimensional Hilbert space. So practically are two distinguishable states, like 0 or 1, or there is current in the system, or there's no current, high voltage, low voltage, and things like this. So there are superpositions, which means a strange state, non-classical state, like 50% that the state is up, 50% the state is down. So therefore, in quantum information, beyond standard classical states like 0 and 1s, we have also those special quantum states, in a sense, a little bit of up, a little bit of down. So a combination or superposition of 0 and 1s, and then quantum information is powerful because we can use of those larger space of states and create algorithms which use quantum entanglement. Again, entanglement is like superposition for bipartite systems, 0, 0, plus 1, 1, and create algorithms which sometimes are able to produce the required outcome faster than in the classical world. So there are some concrete, more technical questions about quantum entropy and how it behaves. So basically, entropy is a very general notion in thermodynamics in different branches of physics. In information theory, it is the measure of how well we can predict the outcome of measurement. For instance, if we had a coin with two heads, of course, then we know that after every toss, we will get a head. So then the entropy is 0. For the standard coin, unbiased coin, with such that with probability 1/2 you get head or tail, then the entropy is maximal, because we cannot predict if the coin is unbiased what will be the outcome. So here entropy is the measure of how well you can predict the result of measurement, and concerning entanglement entropy, it is the measure of correlations between both subsystems. So indeed, it's written here that for macroscopic object like my pen, I don't need any probabilistic approach, because I can exactly measure that the pen is here, and probability, of course, it can oscillate a little bit, but then up to precision of my measurement, there are no probabilistic effects are not important, they can be neglected. However, it is not the case if you consider very small particles. What means very small? Very small means that the action, so action is kind of physical quantity, which is like product of momentum and position, is of the order of the famous Planck constant, written h bar, so h over 2 pi, which is a really very small quantity. So another question, what is the use of entanglement in quantum error correcting codes? Okay, so classical error correcting codes, this is simple. You give some redundant numbers. For instance, if you have any book, there are some special book numbers, so you can identify every book. Let me see. Okay, I have here a book. Yes, there's some number, and then there are a little bit more numbers. Some are redundant. Just if you change one of those digits. So here's such a standard code of books, and there is some redundancy. There is some error correction. If you skip one number or maybe exchange 2 digits, you can decode that there was an error. So similarly, if you have a quantum information stored in qubits, so there are many qubits, like some of them are, for instance, in state up, some of them down. The quantum error correction means you encode, for instance, 1 qubit in the space of 3 or 5 in such a way that if at least 1 qubit will be flipped, there will be an error, you can still encode quantum information. And therefore, entanglement is crucial, because those quantum error correction codes rely on quantum entanglement. They are created using entangled states. There was another interesting question about the relation between quantum information, quantum theory, and black holes. So you might think they have nothing to do in common, because black holes are basically very massive. In fact, large objects far away. Quantum theory concerns very small scales. However, if you go into details, it happens that even in black holes, some quantum effects may play important role. We learned that the black hole absorbs basically everything, matter, but also radiation. However, the famous result and effect of Hawking, which is called Hawking radiation, means that even black hole can radiate, because at the horizon of the black hole, there might be a creation of entangled particles, and one part will go to the center, one will be expelled in form of the radiation. So eventually it will carry out some energy out of the black hole, and in this way, due to quantum effects, the black hole will lose its mass. Of course, it will happen at a very long time scale, so those quantum effects are still not so important at the shorter time scale. Well, there is question, do the qubits have directions? So look, qubit is just a system you can describe like a quantum version of code. So qubit itself does not have a direction yet. However, if you have a well precisely defined state of the qubit, it can be visualized as a vector with a given direction. For instance, let's say 1 is pen up, 0 is down, and this superposition state is oriented here. So you see a concrete state of a qubit can be associated to a vector which has a direction. So there is, okay, another technical questions about CSS codes. Yes, they use entanglement. So the question was whether they use entanglement, but maybe this is too technical. So there's another more general question about quantum fields. So, well, one thing is we consider a matter like particles, and then we consider field, which is a space. Field means properties of the space. So quantum theory of fields is basically theory of space at the short scale. And then particles can interact between them just by exchanging fields. So there was a question how quantum theory can be helpful for the improved research activity, and were a couple of questions related, let's say, quantum technologies. So in short, if you have a standard watch like this, so it's also there are quantum effects here concerning the liquid crystals, which allow us to see the numbers. Also in your cellular phone, there are many devices using quantum effects. And this is known for, let's say, since the transistor was discovered after the Second World War. But recently it happens that quantum effects may be used for diverse quantum technologies. And now there is a new field of mesoscopic physics. What are mesoscopic systems? You know the word meso, something not too big, not too small. So mesoscopic systems are such systems which are already not microscopic, they are already, well, almost large enough, but still they have some special properties that quantum effects are still there, and they play an important role. So in a sense, there are such systems which are already not so very small, however, for which quantum effects are important and can be used in technology, in industry. By the way, concerning India, I recall now there's famous effect which is called Bose-Einstein condensate. So, of course, the first name is a well-known Indian name, and then it means there's a condensation of atoms which form such a special kind of matter in which the motion of those individual particles, atoms, is correlated. So, in a sense, they exhibit quantum effects. Now a question, how anything can be unentangled? Well, another statement. If you have those two particles which interacted, and due to interaction, some entanglement was created. Now, if we even put those two particles apart and they perform measurement, due to entanglement, the outcomes will be correlated. So again, entanglement is correlation between some systems. However, this effect, quantum entanglement, is destroyed due to interaction with environment. So if we have even light shining on those two entangled particles, the entanglement will be destroyed, and eventually will vanish, because those two particles will basically become unentangled. So in a sense, due to interaction with environment, with the outside world, entangled particles will become unentangled, which basically means that therefore working on quantum computation and trying to perform quantum algorithms, it is not simple. One has to hurry up a bit to make use of entanglement before it is destroyed, and practically one does it in the very low temperatures, just to shield, to protect the quantum information from, let's say, thermal noises from the interaction with environment. So there is a question, how long entanglement is very nice question, was already checked in experiment. So exactly it is this scenario: you create entanglement, you allow those two subsystems to go apart, and then in the you can produce photons, which are pair of photons which are entangled, and then somehow it is possible to send those entanglement photons for distance of couple kilometers, then it was like of the order of 100 kilometers. And recently there were even results in China that they managed to send to couple the satellite at the orbit like a few hundred kilometers above the Earth with Earth and submit and send entangled photons. So the entanglement was still preserved for such a distance. So how much time do we still have? Is there still some time left?
Carol, I think maybe we should wind up. I think it's 5:50 and the other session would have also started.
Yes. So let me thank all of you for questions. I'm really sorry I was not able to answer all of them. And I'm very pleased that so many of you participated and wrote questions. Now, Arul, how is it? Would you be or me able to write some, type some answers after the session is closed?
That I'm not sure whether we could.
Because some people were interested to get some hints how to proceed learning more about quantum entanglement. So what would be your advice?
I can take care of it. Maybe I should just tell people that they could email, for example, they could email me and I could, or any of the panelists who are here, and we should be able to answer. Is there anybody from the Office of Global Engagement? Do we have some?
Yes,
we will email you all of the questions from the participants.
Okay.
Perhaps amongst you and the rest of the you could respond to them at your convenience.
Okay. So then let me thank again for the invitation and for the possibility to talk, to be here with you. And I hope I will visit India again by some other time. Thank you. Thank you again.
Well, we thank you very much, Carol. I mean, it was lovely of you to come and, answer the questions. And, so indeed, I should tell those who are here that we've had the pleasure of having Carol here not long ago, and we hope that you'll be visiting our center actually and interacting with us more. And yes, Carol, thank you very much.
Thank you. Thank you very much.
Thank you a lot, Professor Carol. Thank you, Professor Arul. As you can see, we've got more than 100 questions from the participants. So thanks for spending all this time talking about quantum physics and everything that we've discussed so far. And I will email you all the questions so that you can respond to them. Thanks a lot. And for the participants, we have the other webinar has just started. So you could be a part of that as well. So thanks to everyone on the panel. Thanks a lot.
Thank you.
Thank
Goodbye.
you. Thank you, Rachel. Thank you, everyone.
Thank you.